Welcome back to IT 3000. Today, Episode 9, the kernel. At its heart, the kernel is defined by one thing: privilege. It's the single piece of code on your machine allowed to do absolutely anything, and everything else, every app, every driver, every process, has to ask it for permission. So let's pin down what that actually means. The kernel is permanently loaded in memory. It runs in the CPU's privileged mode, and it sits between every process and the hardware underneath. Nothing touches the disk, the network, or another process's memory without going through it. In one sentence, everything else gets things done by asking, and the kernel is what makes the asking mandatory. So let's pin down what that actually means. The kernel is permanently loaded in memory. It runs in the CPU's privileged mode, and it sits between every process and the hardware underneath. Nothing touches the disk, the network, or another process's memory without going through it. In one sentence, everything else gets things done by asking, and the kernel is what makes the asking mandatory. Now, once you accept that privilege is the whole game, the natural question becomes, how much code actually deserves it? Different operating systems answer that differently. A monolithic kernel, like Linux, says everything belongs inside: drivers, file systems, networking, which is fast but fragile, because one bad driver takes down the machine. A microkernel, like QNX, says keep the privilege core tiny and push drivers out to user space, trading speed for robustness. Hybrids like Windows NT and Mac OS split the difference, pulling hot paths back into the kernel, and unikernels drop isolation entirely: one app, one kernel, one image, because if there's nobody else on the machine, there's nobody to protect it from. So where does that privilege actually live? On x86, it's baked right into the CPU as a set of numbered rings. Ring 0 is the kernel with full access to the hardware. Ring 3 is where your applications run, asking permission for anything interesting. Rings 1 and 2 were meant for drivers and services, but almost nobody uses them anymore. And Ring 1 sits below the OS entirely for the hypervisor. The crucial point: the CPU enforces this in hardware. Code cannot simply decide to promote itself. Privilege escalation is the art of breaking that rule, which is exactly why it's the most valuable class of exploit there is. So how does an application actually cross that boundary? Through a system call, the one sanctioned doorway from Ring 3 into Ring 0. It goes like this: the program loads a call number and arguments into registers and executes the syscall instruction. The CPU flips to Ring 0 and jumps to a fixed entry point the application has no say in. The kernel then treats every incoming pointer as potentially hostile, validates everything, does the privileged work, copies the result back, and drops the CPU back down to Ring 3. The application continues, blissfully unaware it just briefly touched the most powerful code on the machine. Now, three words often get tangled together, so let's separate them cleanly. The kernel is the core itself, loaded at boot, resident until shutdown, and swapping it out means rebooting. A module is code that gets pulled into the running kernel on demand, and it inherits full kernel privilege the moment it loads. A driver is just code that talks to one specific device, usually shipped as a module, sometimes compiled straight in. So all three run privileged. The difference is purpose and timing. With that foundation in place, everything else in this series builds outward from the kernel boundary. System calls are the formal way user code asks for privilege. Device drivers and interrupts handle the conversation with hardware. Virtual memory, context switches, and hypervisors all exist because the kernel has to juggle many things safely at once. Next up, the system call, the doorway itself. So, three things worth carrying with you. First, every kernel architecture, monolithic, microkernel, hybrid, or unikernel, is really just a different answer to one question: how much code deserves full privilege? Second, those privilege boundaries are enforced by the CPU itself. Software cannot promote its own rights. And third, modules and drivers are related ideas but not the same word. Keep them distinct. The kernel is the privileged core everything else asks permission from. I'm Dargslan. See you in the next episode. See you in the rocket, yo.